Okay, so first let's okay. Let me first say something about the yeah. So let me first say something about quickly about the harmonic oscillator again, and then get back to coherent states. So the harmonic oscillator. So we had. Remember, I started out by the standard kind of description of this thing uses the state space L2 of R, and then either either in the Q version or the P version related by Fourier transform. And then what I wanted to use the harmonic oscillator as one motivation for introducing a different kind of state space, which is what I'll call, what do I want to call this? Let's call it, when I'm specifically talking about it, I'll often put a BF, I mean the Bargmann-Fock thing. And what it is, I explained last time, in some sense, it's holomorphic functions at C. It's functions that depend on Z and not Z bar. And it's got, I guess I won't write it down again, but there's the other thing you have to do is, in order to specify the space, here when you say L2, you mean you implicitly mean the standard inner product on complex functions on the real line. Here, I want to, I won't write this down, but this is, again, this is this thing where you integrate over C. So, anyway, you integrate over C. Well, right, but it's just this Bargmann-Fock thing. It has this weird feature that it's this guy complex conjugate times this guy is a function of Z, but then you have to put in some Gaussian in order to make it to get a convergent result. But the idea is that all of these things, so these all carry Lie algebra. Representation of the Heisenberg the Heisenberg group, which is the thing that's got a basis. Lie algebra has got a basis Q, P, and 1, and the Lie bracket is the Poisson bracket. And but what's actually, if you want to you can in this case. So if you're going to talk about these things, you've got Q and P operators. I mean, if you want, you can complexify. In other words, you can throw in, instead of taking real linear combinations of Q's and P's, you can take complex linear combinations of Q's and P's. And so, I mean, you can do that if you want. Here, it doesn't really tell you anything new. Here, you kind of have to do it. You have to, because here you're going to have. You have to take kind of complex linear combinations of Q and P, and you're going to use this homomorphicity condition. So you have to use the fact that it's complex. So here, so when you do this, you're automatically complexifying the Lie algebra. And this is something. I mean, whenever you're talking about Lie algebra representations, you're always free to take your original real Lie algebra and look at complex linear combinations of these elements. And this is what you do even when we were talking about representations of SU2. If you want to construct raising and lowering operators for SU2, again, same thing. You have to complexify. You have to take complex linear combinations of the real things to get the operators you want. But here again, you kind of have to do it. And let's see. So we want, but the okay. I don't know if I want to say anything more. But the what you're given here is you're actually given a real Lie algebra and a a complex Lie algebra, which is the same thing. You're just extending the real scalars here to the complex scalars. That's that's really all that's going on here, and it's pretty simple. And so you can the relation. So in terms of these operators and these in terms of these operators, you often can just go back and forth. Just use the well. Anyway, there's the formulas relating Z and Q and P, and relating a dagger and capital Q and capital P. Those are fairly simple. What I want to get to later today and what I explain is the relationship between not between the operators but between the state spaces, and the relationship between the state spaces is quite non-trivial, as I kind of mentioned last time. That this is not there's a unitary transformation relating these two things, but it's a non-obvious one, and I want to try to get to the point of writing it down. So okay, so this was the underlying thing we're looking at. And then I wanted to talk about coherent states. And maybe just to give some kind of, so let me give some kind of motivation. Give some motivations for why you want to think about these things. Well, one, I mean, there actually is there's physical motivations if you want to. And I mentioned this one last time. If you want to describe the state of a if you're doing quantum optics, you want to describe the state of a laser. So if you have this kind of there's this notion of kind of a coherent quantum state. That's kind of and studying these things is kind of the origin of a lot of this formalism for people studying coherent states. But the other things that I wanted to do with it, one is you can relate. I'll explain this. You can it's related to Bargmann-Fock. Okay. So the coherent states are so ultimately what I want to do is I want to figure out how to get from states in this formalism to states in states in this picture to states in this picture by some unitary transformation. And one way I'm going to do it is going to be go via coherent states, because you can understand how coherent states are related to these guys, and you can understand how Bargmann-Fock states are related to coherent states. So going via coherent states, you can see what the relationship between these two things is going to be. And then there's a third application, which is I'll say something at the end, is the harmonic oscillator propagator. So I'll explain this at the end. And so what this is about is if you want to figure out if you know that your initial state is some kind of delta function at a certain position, you know that at a certain position, and you know that you're going to evolve as a quantum harmonic oscillator, then you'd like to know what at some later time you'd like to know what the amplitude is for being at any other point. And that's I'll say that's what this propagator is. And it turns out that that's actually to do that calculation, expressed in this language, expressed in terms of functions of Q or even of P, it doesn't matter. The answer is actually very complicated, and I'll explain why. But in some sense, the answer to this question is much easier if you write it in terms of coherent states. I think I started. I've been actually. I think I said this last time. I think the last time I wrote down the formula for how a coherent state. The fact that a coherent state under under the harmonic oscillator Hamiltonian, it evolves coherent states stay coherent states, and basically the coherent state is just given by a point in phase space, and that point in phase space just moves around the way that the classical Hamiltonian would move it around. So the other reason for talking about coherent states is that they make the calculation of the harmonic oscillator propagator becomes something very easy and something very trivial in this language. And then if you understand the relationship between coherent states and Bargmann-Fock, then you know how to that tells you how to get the story about the harmonic oscillator which is easy in coherent states and write it back in original physical space. The fundamental problem is what you've done. If you try and use one of these, you have a nice intuitive idea of what's going on through wave functions that depend upon space. But what you've really done is you've broken this beautiful symmetry of the harmonic oscillator between Q and P in phase space. And that's the great thing about Bargmann-Fock is that it doesn't do that. It doesn't break up this nice symmetry between P and Q. It's just because that's just the rotational symmetry in the C. Okay, let's see. So let me quickly then go over what the coherent state story is after this motivation. And I started by giving another kind of a mathematical motivation for it, that the coherent states were the things that you got if you took the harmonic oscillator ground state and acted on them with the Heisenberg group. I mean, this whole state space is a representation of the Heisenberg group you act on. So you act on these states with, you take this distinguished state, which is the ground state, act on it with a Heisenberg group, you get a three-dimensional family of states. If you kind of ignore the overall phase information, it's kind of up to phase information. It's a two-dimensional family of states. That's the coherent states. So anyway, and so the definition, there are various definitions, but the one that I gave was this: is that alpha. So alpha is just some complex number, and this is going to parameterize again. So this is kind of, we're going to parameterize the coherent states. It's going to and it's in some sense there's this extra variable of the phase information, but I'm kind of mostly trying to ignore the phase of these states. So you should really be typically thinking of states kind of up to an overall phase. And but one definition of this guy is this: it's the e to the alpha a minus alpha bar a. And I tried to motivate this. This operator is the operator you get by, this is an element of the Heisenberg group acting on, it's not the Heisenberg group representation, but acting on this guy. Okay. And there's some noise outside. Does that cause much trouble hearing me? Sorry. Okay.
No, you're all good.
Yeah, it's probably better. You got the mic. I have to listen to them, but anyway, hope they'll stop. Okay, let's see. So where was I? So that's, and then the crucial fact. A alpha. So these guys are eigenvectors for the annihilation operator with eigenvalue alpha, but it's crucial to remember that A is not self-adjoint. So you can't set A is not an observable. A is not something you can all this business about observables and operators, it doesn't apply to A. It's not self-adjoint. And then you can also calculate Okay, and then what now? Now, one important aspect of these things that you can calculate is that you can get the relation. You can easily get this to get the relationship between these states and the states with a certain occupation number. So you also have alpha is equal to e to the minus alpha squared over 2 Okay. Okay. So what this guy is, he's actually, if you think of him in terms of states with a fixed number of quanta, he's an infinite sum of states with 0 up to infinity quanta, but with these very particular coefficients. Okay. So this guy definitely does not have a fixed number of quanta. He's not a anyway, he doesn't have a fixed number of quanta. He's not an eigenvalue of the energy. Okay.
So question on that screen. So then, just to make sure it's annihilation operator acting on.
Excuse me. Sorry, Leo.
Can you hear me now?
I'm really trying to see what these guys are. I don't know what these guys are doing out there. But anyway, just speak loudly. I think I can hear you as long as you can hear me. So.
Okay. So yeah, question about like the series. So it doesn't So if for n greater than for the index greater than the actual n of the state, then they will just annihilate, right? So it only matters up to some finite number of terms.
No, I mean it's an infinite sum.
But then, because we're doing annihilation operator n times on the state, n, right? So then 4.
Yeah. So n is something like a dagger applied n times to 0, and then you've got there's a normalization of it.
Yeah. Like if we add annihilation operator on it more than n times, then it would just get 0. So all the higher terms doesn't matter, right?
The annihilation operator doesn't give 0. The annihilation operator takes you back to the same thing. So this is kind of carefully set up so that if you act with the annihilation operator, all the coefficients are stuff that the infinite sum shifts by 1, but it's the same infinite sum up to a factor of alpha. Yeah. So this is not. If you act more and more times with the annihilation operator, you'll just get more and more factors of alpha.
So I'm not saying the annihilation acting on the coherent state. Here you're acting on the the normal number state, like the eigenstate of the infinite, right? So then if you act on it more than the number of times it is above the 0 for energy, then
so you're just saying AM n is equal to 0 for m greater than n, right?
Yeah, exactly. So I'm just saying, for that sum, for the index n greater than the actual number of the state n.
But what's wait, sorry, this is alpha.
Oh wait, this is alpha.
Sorry, that's what you mean. Sorry, this is alpha, not A. Alpha. Yeah. So this is just the number.
Oh, okay. I missed that.
Sorry. Yeah. So it's in the definition. Well, anyway, there's a calculation to get from here to there, but it's that. Yeah.
Okay. Yeah.
I see why you're confused. It was because of. Okay. Now, so what I want to do, Okay, so there's a little bit of a funny, so the question, what I was trying to get at in some of these calculations in this section, some of which get a little bit obscure, is that I was trying to get at the question of, one question is, what is the analog of a delta function? Or in here. So if you're used to doing kind of calculations with this kind of Dirac formalism, where you talk about these distributional states Q, and then you use and then you think about so then psi of Q, you think of the wave function as being some abstract state, but then it's coefficient with respect to the eigenstate with the eigen. Anyway, to the delta function at Q. So if you're used to that formalism, you can ask kind of what's the analog of these states that would satisfy this. What you do is so if you define delta W to be equal to well, there are various ways of writing it down, but maybe you write it down as sum from n is equal to 0 to infinity W bar to the n over square root of n factorial, and or this is also, you can also write this as just in terms of, in the Bargmann-Fock representation, it's going to be e to the W bar Z, and it's going to be it's also e to the W squared times the coherent state. I mean, there are various ways of writing the same object down. But what it is this is remember is this is non-normalizable. So it's a state which it's kind of close. It's kind of like one of these coherent states, except it's got this e to the e to a positive not number depending upon W. So this thing causes it to be non-normalizable. Then it has this gadget has this nice property that it's called the that it has a delta. Then you can compute delta Z W and get, anyway, there's a calculation you have to do, but it's something you're taking the inner product of this guy with this guy, and so you get an e to the Z W bar, e to the minus W squared, psi of W uz bar, sorry, dW. And if you calculate out this integral, you can show that this integral is equal to just psi of Z. Sorry, no, what have I done? Oh, sorry, this is psi here. So you get something. You get kind of an analog of this formula that an arbitrary psi. If you want to figure out in the Bargmann-Fock representation what function of Z is that, well, you just you take the inner product with this guy, with this gadget. You take the Bargmann-Fock inner product with this guy, and you have to. But the problem is that this is kind of like a delta function. It itself is non-normalizable. And sometimes in the mathematics literature, this, doing this gadget is actually has a name. It's called a reproducing kernel. because you feed it a function, and in some sense you get back the same function. So it's called the reproducing. It's called the reproducing kernel. But even for better or worse, I kind of used this gadget to try and do the calculation, relating the Bargmann-Fock representation and the Q and the standard position space representation, and the way I did this. So this is a bit of a mess. So, I'm not sure I want to write down all of this, but if you look at equations 23. 2311 and 2313. Let me just say something about them. So there's the full derivation of equations 23, 1, 13. And so there, what I'm doing is I'm calculating the so I calculate I get the relationship between a coherent state in this Q representation, and so this, remember, is anyway. So let me just show how this starts off. This starts off as start off with this way, either. To e to the dagger. Yeah, and then I use a dagger. Use a dagger in the Q representation. It's there's a square root of omega Q minus 1 over square root of omega dq. So I use the fact I do that in the Q representation. It's this, and anyway, and you work and you know what 0 is e to the minus 2q squared. So you could do this calculation, and you end up with this kind of slight mess that it's there's an omega over pi quarter, and there's an e to the minus alpha squared over 2. Then there's an e to the weirdly there's an e to the minus alpha squared over 2 with no absolute value, and then an e to the minus omega 2 over 2q squared. You get that. And then there's an e to the square root of 2 omega alpha q. So anyway, so you could do this. It's a bit of a mess, but it's not that bad. But this is the basic equation that tells you how to what coherent states look like in position space. So I told you what coherent states look like as a sum over occupation numbers, is this infinite sum. If you want to know what they look like in Q space, it's this weird object. And inherently, these are things which can behave nicely in Q and P. You kind of force them to just look at wave functions in Q space, and then you end up with this mess. Okay, so that was 2311. Then what I wanted to do is then the okay. Oh, and then you could do this. I could do the same thing for that. Instead of working with this alpha, I want to work with the analog of Q, the analog of the delta function for the Bargmann-Fock case, which is this Q, and I guess I called it delta. I guess I wrote it down. Where did I write this? Yeah. So then I wrote down Q delta. So you can use that. You can use this to evaluate. Let me call it let me use u for the variable here, and you get, so this is equation 23, this is 2311, this is 2313, and this guy comes out to be omega over pi, the quarter, then e to the minus u bar squared over 2 e to the minus omega over 2 q squared, and then e to the square root of 2 omega u bar q. Anyway, it's these guys are simply related to these guys by this normalization, and so anyway, you get this thing, and then what I wanted to do with that, the whole point of that was then to tell you how to get from so the unitary transformation taking let me see what I say it here. Psi H L2 to Q R Q to what I'll call to an element HBF it's called the Bargmann transform. And it's written. What it is it's psi goes to what I'll call b psi, and b psi is a function. So this is going to be a holomorphic function of z. So this is some function of q. This is the position space thing. If you want to know what's the what's the holomorphic function of z in the Bargmann-Fock fit space, it's this guy. It's what you do is you evaluate integral from minus infinity. You basically use the fact that these guys here are have a completeness relation, and they have this reproducing kernel relation, and you can that they behave like delta functions, and so you can write this down. Well, actually, no, sorry. So actually, all I need to do it in this direction is just to say that it's this guy. I'm going to integrate over Q. So I'm just going to do the standard, use the standard kind of completeness of the Q eigen formal eigenstates, and say what is it? So it's Q delta Z Q. And then Q psi, okay. And then and then you get a slightly awful form. No, actually, it's not that bad. So okay, so the formula you get is this one then, and this is 2314. So this guy, this is just psi of Q, and then this guy here is what is just the conjugate of what I had here. So it's actually what it is just omega over pi to 1/4, and then e to the minus z squared over 2, and then there's an integral to infinity e to the minus omega over 2 q squared, and e to the square root of 2 omega. There's a zq and psi of q. Okay. Anyway, so this finally is the answers this question as to what's the what's the relationship if you know psi of q, what's the what's the Bargmann-Fock wave function as a function of z? And the claim is that this is, I mean, if you do a little bit of work, you can also write down the inverse of this transformation. You can show that it's unitary. There's a lot of, anyway, you have to show that this actually gives you a holomorphic function of z, and that it's that it preserves the norm squared of this thing is the same as the norm squared of this thing. The norm squared of this thing in the L2 norm is the norm squared of this thing in the Bargmann-Fock norm. And so it's, anyway, this is really a nice unitary transformation. So it's kind of a weird, anyway, it's kind of a somewhat weird piece of mathematics telling you that the L2 space of these is related to this space of holomorphic functions by this kind of somewhat surprising transformation. Okay. So that's this is a little bit of a horrible calculation, but it's kind of it really is kind of inherently horrible because you're going from, anyway, this Q thing really has just kind of, by writing this thing here, you've broken all the nice QP symmetry, and you have to kind of do something to kind of get it back. Okay, so then now the applications. Okay, so the main one of the applications I wanted to do with this, which I tried to do that, and I didn't. If you look carefully in the book, you'll see that I didn't actually really work out the full details of this calculation, because this is kind of a surprisingly horrific calculation no matter how you do it. But let me kind of state, I mean, the problem is very obvious. But let me state down what the problem is about the propagator of the harmonic oscillator, and then I'll explain how, there's a conceptually straightforward way to get it using this stuff, but to actually do the calculation involves some of the world's most horrendous manipulations of kind of Gaussian integrals. So I don't. But the problem is that there are every other way of getting it also has problems. Let me. Okay, so let's see. Here's the. Okay, so the harmonic oscillator. Propagator. And maybe, but before I do this, maybe let me just go back and remind you what. Okay, so what this is. So the problem is that you basically want to what the problem the propagator answers is if you start out at time t or time t is equal to 0, knowing exactly where something is, what is it? Then what's its wave function going to be at later times? So what you do is what you want to do is you want to compute if you know that you're at Q0 at time 0, you want to evolve by the Hamiltonian for time t, and then this is going to give you some wave function. And if you want to think of that wave function in position space, you want to know what the value of that wave function is at any point, at some point Q1. So we want to find, as a function of Q0 and Q1, we want to evaluate this function, and this is the propagator. And what we did for the free particle. So what you do with this, so your problem here is that this is a complicated operator. If this operator was a diagonal operator, then this would be an easy calculation. So what you want to do is you want to change representations to where this operator is easy to evaluate, or where it's easy to evaluate. And in the for the free particle, for the free particle, h is just p squared over 2m, and so this is diagonal, and this behaves nicely in position space. So what you do, for the free particle, you write this as as the integral minus infinity to infinity over all possible choices of p of these guys. H. Zero. Or, I mean, this is just a way of, so we basically just Fourier transformed, we just really Fourier transformed to momentum space, and then this becomes, this just becomes the function either on these states, this just becomes the function e to the minus I p squared over 2m t, just a function as opposed to the as an operator. And I'm being a little bit sloppy here, but this is anyway. This is basically what you're doing when you're just Fourier transforming to momentum space using the fact that it's diagonal, and Fourier transforming back, and then you get what you get. You end up only needing to do. Or you end up just getting a p integral and something like and the integral from minus infinity to infinity e to the I. I'm not sure about the sign of this, but it's just q1 minus q0 p e to the minus I p squared over 2m. So you basically do this. So this is the calculation. We kind of went over this before for the free particle, and there's something very very funny about this guy, is that you notice that you're taking the Fourier transform of something which definitely the Fourier transform of this guy is definitely not a function. So there's a lot of subtleties here that this is a this gadget here has to be interpreted as a distribution. So in the free particle case, the propagator is definitely not a function in any sense. It's a fairly tricky distribution, but it's the Fourier transform of something very simple. Okay, so for the harmonic oscillator, okay, so what you want to do with the harmonic oscillator is you want to okay, and this is what I say a bit about this, and where is it? Okay, so for the harmonic oscillator, what we're going to do is instead of going to p basis, go to use coherent states. And I wrote this down. I think last time I wrote down what happens with the Hamiltonian acting on a coherent state. It just up to this phase. It just it rotates the complex number in the complex plane the way that the way that q plus ip would evolve. And then what you find is that for coherent states, if you start out at a certain coherent state, and then you evolve a ht, and then you end up at some other, let's call this big T for time, but alpha t. So if you take a coherent state and evolve this, and then take the inner product with some other coherent state at a later time, you end up with something. It's a little bit of a mess, but something that isn't too bad, because anyway, you can. I think last time I wrote down the formula for what this guy looks like, and you have to. You can use that to evaluate this inner product, And this is, and you get this expression. It's like e to the minus a half, and some of these guys, you get an overall factor of that, and then there's a the funny business is this guy 0 e to the minus I omega t minus, and then there's the minus I over 2 omega t. Okay, and the funny thing, and all of this is actually, sorry, yeah, that's right. This has the minus half is there. So so all of this mess it is up in the exponent. So this is kind of a normalization factor. This is just the thing that keeps track of that extra phase coming from the fact that the ground state has energy a half omega, and then this is the real thing. It's just telling you that, you know, as time evolves, alpha 0 is just getting multiplied by e to the minus omega t. So in the coherent state basis, then you can you can evaluate the propagator in a fairly simple way. Now what you have to do now, the mess is so to get, so the idea is that you can then use the use these formulas that I was writing down before, or the Bargmann transform in whatever form you want, and you can go and change from here back to the Q basis, and from here back to the Q basis. So you end up with a fairly horrible calculation in the P space. You ended up with a you know, this in the P basis, the Hamiltonian is fairly simple. Here in the P basis, the Hamiltonian the Hamiltonian is just this phase factor, but it's a bit of a complicated, much more complicated mess. And then in the going back and forth between the P and Q basis just involved these Fourier transforms and these factors of e to the IQP. Going back and forth between this basis and the Q basis, this basis and Q basis, involves those much more horrible factors that you saw in the Bargmann transform. So conceptually, this is what's going on. So you can use this to get UT okay, but I won't I won't try and write it down. So I write down the answer in the book. It's equation 2312. But to be honest, I don't actually complete the calculation because it's one of the worst calculations I've ever seen. If you try and calculate this thing and do the Bargmann transform and the inverse Bargmann transform to it on either side to get you to here, you end up with having to evaluate a whole bunch of really awful Gaussian integrals, and you get anyway. There's a standard answer to this guy, but that's. Let me just start. So that was kind of where I wanted to end up. Unfortunately, I think when I started thinking of doing this, I thought that maybe these. I thought that this might actually make the calculation kind of easier. I think this actually kind of makes the calculation conceptually straightforward, but in terms of the actual details, it's pretty awful. The other ways of trying to calculate this is that instead of going from Q space to coherent state space, evolving with this and coming back, you could go from Q space to the energy to the occupation number space, and then the evolution is also very simple, and then you can come back. But the problem is that the going from Q space to the occupation number space, you get these Hermite polynomials. So if you try and do the calculation that way, you end up with kind of having to do some very tricky calculation about properties of Hermite polynomials. I mean, but that also works. That's another way of doing it. And there's a couple of other ways of doing this calculation, but there isn't really a simple one. So anyway, but I don't want to just take the time to write it, but that's the anyway, you can see what the end result is in equation 2312 there. Okay. Anyway, so I think maybe that's where I want to stop with this. So this is kind of the end of kind of what I wanted, and the new material I wanted to cover this semester. And but let me say, but first, before I go on, are there any questions about these coherent states or about the harmonic oscillator propagator or any of this? Because then I'll go and spend the end of this just saying a bit about what we've been doing and where we're going with them. Okay, and I'm sorry. I mean, this is a bit of a mess, but it's it is a kind of a anyway. It always kind of surprised me how the harmonic oscillator is supposed to be the simplest thing in the world. But the fact that this is a fairly complicated gadget is always a bit surprising to me. Okay, so let me just kind of now quickly kind of say some general things about what we've been doing this last semester, and about kind of what the and also that I want to kind of say where this is going, about why what I'd like to, why I've kind of done some of these things, because what you can do with them next semester to try to get some of the most powerful ideas about modern physics. So. Okay, so the point of view I was taking was this. So this is just an overview of what you've seen. Is that from some fundamental mathematical point of view, quantum mechanics involves is really about that your state space of a quantum mechanical system you should think of as being a unitary representation of various Lie groups, and more importantly, that they're Lie algebras, the infinitesimal representation, and it's those, and it's these guys, it's these Lie algebra representations that's going to give you your a unitary Lie algebra representations are going to give you your self-adjoint operators that are going to be your observables of the theory. And then so the examples. Okay, so we did some general theory, yeah, of such representations. And in particular, we started with we did for U1. We talked about if you have this kind of simplest Lie group, which is just the rotations in the plane, U1, we kind of answered the question of what's the algebra look like? What do all the unitary representations look like? We kind of solved that completely. Then we went on to some more interesting groups that were non-commutative. So they're more interesting, SO3 and SU2. And then the other thing we did there, then we also did E2. Well, anyway, let me tell you. So we did these kind of these guys, and this I should say is the beginning of a long theory which we didn't go into, which is what you'll often see in mathematics classes, which is if you start taking larger, higher rank groups, what happens. But we just stuck to these cases, and these were cases where everything breaks up into irreducibles. The irreducibles are finite dimensional, and you can analyze exactly what they are, and they end up being important in physics. But then what we did was we looked at the at the Euclidean groups, so E2, and E3. And E3 was these are the translations, or maybe I could have also I could say that we also at some point also looked at the translation group. But this is a fairly trivial representation story, but we talked about that. And then we put some of these together with these and looked at E2 and E3. So we and I kind of explained it, exactly kind of what I kind of wrote down what all of the irreducible representations of E2 are. Now they're infinite dimensional representations, and for R3 and SO3, I think I maybe at least stated at some point what the full list of irreducible representations are. But we looked at we found that among these irreducible representations, one of the ones was that this gave you the so here is a free particle. Well, fix and in order to get an irreducible representation, you have to fix the energy. So if you fix the kinetic energy of your free particle, then you get an irreducible representation of this group. We looked at in the kind of this and so E was these irreducible representations were labeled by this E. That was the value of the first Casimir operator. And then I said a little bit about that you could also have. So you also have helicity. And Z. So so this was the helicity 0 case was just our standard free particle, and that there were these higher helicity cases which I didn't say very much about how to construct, but these also existed. But the story about the story about kind of what are the possible kind of non-relativistic free particle theories that you can use, that you could come up with. It really is essentially the same problem as what are the irreducible representations of the three-dimensional Euclidean group. What are the things? Because you're basically the fact that you've got translations and you've got rotations, and they're combined and they act together in this way. Really forces the structure of what a free particle theory has to be, to something very specific. And what and then in particular we had, so it's all kind of forced by the fact that these guys are these momentum operators in the algebra, and this part of the representation gives you the angular momentum operators. So the basic operators you have, saying that you have an irreducible representation of this guy, irreducible unitary representation means that you've got self-adjoint momentum and angular momentum operators that obey all the right commutation relations to be from in this group. Okay, so then that's sorry. Now the next this was at this level. I actually kind of was telling you something about kind of what are all the represent. I'm telling you a fairly complete story about these groups and their representations. Now what we want to do, the next thing that we wanted to do was to find some actually kind of deeper structure in quantum mechanics and canonical quantization, and see how to think of that in terms of representation, of a group and representations. So that was really the story of what physicists call canonical quantization. And the stuff that I wrote down before there it's pretty conventional to think of all those objects as kind of symmetry transformations and a story about Lie groups and their representations. It's kind of a bit, canonical quantization is also such a story, but it's kind of less often told that way. And okay, so what this says, what this says is that you have a Lie algebra, which is basically you take function. which is really functions on phase space. Ace and with a Poisson bracket. And now, it turns out that what you could do is you can take that there's an interesting canonical quantization that says there's a really interesting infinite dimensional representation of this in the algebra, which has these properties. So it's a representation on let's take it on L2R. So let's think of this representation as on wave functions Q or P, and then then this works for so it actually only works for only quadratic polynomials. And these things go to to these operators Q, J, PK, QJ, QK, PJ, PK. Sorry, and then 1 QJ, PJ. So you have all of these operators. So this saying that you've got this unitary representation says that you've figured out a way to get all of these guys to act on this space with the same commutation relations as the Lie bracket relations for the corresponding polynomials. And by doing that, what you've done is you've constructed you've constructed a representation of a group, which is the Heisenberg group in 2D dimensions times the semi-direct product with the SP of with a group called the symplectic group. So this is equal. This is the Lie algebra of this guy. So you constructed a representation of this group on here, and now there's the thing to say here is that at this point I'm no longer telling you about every possible. So if you just look at what, if you forget about this and just look at what the 1 QJ and PJ do, then you've got a representation of this Lie algebra of this Lie group of the Heisenberg group, and then you actually have a theorem saying that up to the constant by which one acts, this representation is is essentially unique. That any way you get it, any two things you find that do that are related by unitary transformation. This is the Stoneman-Neumann theorem. But more generally, once I start throwing in the symplectic group, I'm now, here I have told you really fully what these guys are. But once I throw in this guy, really what I've shown is just that the representation, once you have a representation of this guy, it extends to a representation of this guy, basically because this guy acts by automorphisms on this guy. And then, but it's not it's in no way the most general thing, and that the theory of the representations of this group is a so much more complicated story, which I'm not telling you about. But anyway, this is the, there's this package which comes under the name of canonical quantization, which normally just is told by saying that you've got functions on phase space and you turn them into operators this way. But we're going to do that. And then now what we've done is we've okay. So now so it turns out that in this general picture, the story that I was telling about the free particle and the Euclidean group actually is a subpart of the story, because inside here you have the translations by dimension D, and inside here you have the rotations. Here, where you just rotate momentum positions in the same way, and here, where you just translate in position space, leave the momenta alone. Then you've got, these are inside here, and restricting this representation down to here, the Euclidean group gives you the standard free particle representation of the Euclidean group. the one that we were talking about before. Okay, so now the next part of the story was what about what happens about if so at a potential. So if you add a potential, and so instead of talking about a free particle, you're talking about a particle at a potential. If you add a potential, you typically are breaking the translation symmetry. So you no longer have this as a symmetry, but you may have something else. And so so an example. So in D is equal to 3, the Coulomb V is equal to minus E squared over R. We had that you had this SO3 here. This right here. So this is broken. The translations. This ruins the translation symmetry, but you still have the SO3 symmetry. And then there's the tricky business that we find is that this became exactly soluble because there's plus another SO3, which is which it's comes about in a fairly obscure way because it's not it's actually cubic and actually anyway that's a somewhat obscure story. But in general, if you have a rotationally invariant potential, you'll just have this SO3 symmetry. If you have this very very special one, you get another SO3 symmetry. But now in then we did in D is equal to 1, we did V is equal to R, let's say a half R squared, half Q squared. We did the harmonic oscillator, and then the interesting thing about the harmonic oscillator potential is that it breaks this R, it breaks this R. There really wasn't, SO1 is just it's just a sign flip. It isn't anything interesting, but this has an extra symmetry which you don't see here, but you do see up here, which you do see up here. And so this is why what I keep saying it, to understand the harmonic oscillator potential, you have to go. So now you have to get out of this Q space story and the Euclidean space symmetries that you're used to, and you have to kind of use the fact that there's a U1 symmetry that's up in here, so you have H generates a U1 inside SP2 of R. So this, before, it may have been a little bit until you see this, it's a bit unclear, why you want to talk about these these bigger symplectic group symmetries, because who cares? All you really care about are the spatial symmetries. Well, you don't just care about the spatial symmetries. You also care about this U1, which doesn't appear here, but it does appear here. Okay, and then okay, so maybe that's the end of the story I want to tell at the end of the overview of this semester. And let me just kind of say a bit about what I want to do kind of next semester, and about what you need to do with these ideas to kind of get to get to something much more powerful than what you have here. So what you have here is just kind of a theory of a single particle, and possibly moving around in a potential. And that's interesting, but we know in the real world there's lots of particles, they interact with each other. You can create and annihilate particles. The symmetry of the world is actually the special relativity, not the Galilean symmetry of the non-relativistic theory. So if you want to get all these things to work, what you want to do is, so next semester, so to go farther, here are the main kind of ideas that you want to add. that are kind of based upon the ideas that we've talked about this semester. So the first one is you want to go to a quantum field theory. If you want to find a theory that doesn't just describe a single particle moving around, but describes an arbitrary number of particles, the way to do it is you take as as phase space solutions to a linear wave equation. And so this is going to be some infinite dimensional space of solutions, but it's going to have the it's going to come with a Poisson bracket. It's going to have the structure of a phase space. And so what you do is just think of this is just quantize M as an infinite harmonic oscillator. And so e.g. so the so one basis element of M would be a correspond to a free particle of momentum P Q, and then what you want to do is just this for that one dimension in here, you want to treat that as a harmonic oscillator, and then you get states 0, a state with position P, a state with a P, 2 times P, 3 times P, etc. So for each possible value of the momentum, which gives you one dimension in here, it's gonna give you an infinite dimensional state space, but it's just the harmonic oscillator state space, and the quanta. This is going to describe the vacuum. This is going to describe a single particle momentum P. This is going to describe 2 particles of momentum P, etc. And anyway, so you basically then want to do this. Anyways, you want to do this for each P, and then take, in some sense, the tensor product over all P's. And so you want to kind of make sense of that idea. But the way to think about it is just to say, here's this. This is a phase space. I want to apply. I'm just going to do Bargmann-Fock quantization on it. And the Hamiltonian is the thing. The Hamilton's equations for that Hamiltonian are the things that give you the wave equation. Okay, so that's one idea, and then we're gonna do this for you can do this for you can do this non-relativistically and describe non-relativistic multiple particles just by using the your wave equation. It could be just the Schrödinger equation, or relativistically it could be the Dirac equation, or maybe Maxwell's equations. And so you get the theory of kind of elementary spin 1/2 particles, or the theory of photons, or you get the non-relativistic theory of particles. So that's one thing. The next generalization is generalize. Take E of 3, and then which is the kind of non-relativistic symmetry, and you make a bigger space-time symmetry, which is the Poincaré group, R3, 1. So you extend, put in an extra dimension, and change the sign of the standard inner product, and you get, and then you try and do exactly the same things that I was talking about for the Euclidean group in 3 dimensions. You just do this for this, and you can so classifying, so the era give possible entry part. So in some real sense, if you want to say that, I have a relativistic theory of elementary particles. Really, what you're saying is that I've got a theory where the state space transforms under the Poincare group, and I can somehow in this thing I can identify states that are going to be my elementary particles, and those are going to be given by irreducible representation of the Poincare group. So going through this classification I tried to do in 3 dimensions of the representations of the Euclidean group, if you do the same thing for this guy, you get a somewhat more complicated story, and you get kind of a classification of all the possible relativistic elementary particle theories. Okay, that's that. Then the last part of this, the last new idea that you need is this. Well, okay, maybe you should say. Okay, maybe one other idea is that you could let the Dirac equation splitters so to understand what the Dirac equation. So maybe here's a really abstract way of saying this, is to say that the Casimir h equals d squared over 2m has a square root. So this is the basic idea of the kind of representation theory idea behind the Dirac equation, is to say that, wait a minute, that you can actually find the square root of this thing. In the simplest example, in 3 dimensions, you find that h is equal to 1 over 2m. You could take the Pauli matrices and multiply them, take their dot product with the momentum operators, and square that. And if you use the properties of the Pauli matrices, you'll find that it's this guy. So this thing has a square root, which is this has a square root sigma dot p. So the Hamiltonian is a perfect square. Okay, so that's anyway. That's a basic idea. That's a basic idea, and you want to. And the story of the Dirac equation is really just kind of what happens. You have to kind of go to relativity and work in 3+1 dimensions and ask for and take the analog of there, which is the Klein-Gordon equation, and take the square root of that. But this is a very, very interesting story. And then finally, the last new idea you need is this, is fermionic variables. And then really, one way of saying what you want to do here is you want to replace the story. So the story, you got a phase space with a non-degenerate antisymmetric bilinear form. And what you're doing, what I've done is by quantization, I've produced a, at least in the Bargmann-Fock representation, you can think of this as being you get a representation on polynomials on M. This is just the polynomials in Z is what I'm thinking about here, and that's, remember that that's the, well, anyway, that's the, if you take that, you take all tensor powers of this guy and take the symmetric tensor powers. That's the polynomials. Okay. Now what you do here is instead you you take something which is also going to be a phase space, but it's not going to be a classical phase space. It's called a pseudo-classical phase space. And instead of having this antisymmetric bilinear two form, you have something more conventional. You have just a kind of an inner product, something that's a symmetric bilinear two form, a symmetric bilinear two form. Oh, and this is here you have commutators. You have this thing is given by certain commutation relations, the Heisenberg commutation relations. Here you have a representation on what's called this kind, right, which are called so these are antisymmetric. So instead of taking, you take taking the tensor product of arbitrary numbers of the space, and you look at the symmetric things in the tensor product. Instead, you look at the antisymmetric things in the tensor product. And then you get and here you had a here you had a Schrodinger representation, right, which is kind of essentially a unique answer to this problem. Here you have a spinor. You have an infinite. Well, here you have a spinor representation. So what? So this also finally answers the question of how do you actually construct the spinor representation? Well, one way to construct the spinor representation is do the same thing as and do the same thing that you did here with these commutation relations and constructing the Schrodinger representation in Bargmann-Fock on these symmetric tensors here, and do the same thing but with anti-commutators, and you get a representation on the antisymmetric tensors, and it's the spinor representation of because here you have an SP of 2dr. Here you have an SO of 2dr. These are the things that preserve this. These are the things that preserve this. Anyway, so let me stop here. But these are the basic ideas which I then needed to go further. And once you have all of these, you can start writing down. Anyway, you can start writing down the components of the standard model that you've really got. You've got a relativistic quantum field theory. It's got based on using the a Dirac operator, which is a square root of this thing, and the state spaces, the free particle state spaces you get are anyway. For bosons they're constructed this way. For fermions they're constructed this way, and this gets you a long way towards the structure of the standard model. You then, of course, what then makes it more complicated is that it's not just a theory of non-interacting particles. You then have to think about how you're going to get interactions, how you're going to get forces up between these particles, and that's the forces come in through a story about gauge symmetry, and what typically makes a course really complicated in the subject, if you try and follow it, is that it's once you get the interactions, then you start to leave the region in which you can do everything just by beautiful group theory, and you have to start doing calculations which are not where you can't get exact results from group theory, and it becomes a much more complicated subject. And the infinite dimensionality of these spaces really makes things very tricky. You kind of can't finite dimensional phase spaces, when you quantize them, you get a fairly well-behaved object. If you start with an infinite dimensional phase space and try and quantize it, you get anyway. There's problems. The Stone-von Neumann theorem no longer works, and it's much trickier. Anyway, so that's so I guess that's more than enough for today, and that's enough for the course. But I hope I hope I'll see you, many of you again in the spring. We're trying to go through some of this and just give you some idea of what the connection was between what I've been trying to do and where this is going. But are there any questions? But first of all, I should say before there's almost 2 weeks before into the final. I think 10 days or something, or 12 days. So if you have any questions all about anything, yeah, do just send me an email, and I can most of the time I'm happy to just connect via Zoom. We can talk about any of this, but you should let me know, and I'll be around for a while after this. We can also talk today for a while, but let me know. But are there any questions about any of this general nonsense or about the? Of course. Yeah. No? Sure. Okay, well, if not, anyway, it's been I hope you've got something and gotten a lot out of this semester. It is, I realize it's a huge amount of material to throw at people in a one semester course, but I hope it's been worthwhile. Okay.
Thank you.
Okay, then bye now. Bye.
Thank you.
Bye.
Thank you.
Bye.